Okay, so we need a model that tells us how to get these conditional probabilities. So let's look at a concrete example. Let's say we want the probability of the word will when it's preceded by the words on day 0, the water in Cape Town will. Okay, so this is the 8th word. You can count it out. This is the first word, and dunk, 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 up to word 7. And we want to know what is this probability of the word will if it's preceded by these words here. So one naive approach would be to basically get a very large corpus of text. Maybe you scrape news reports in South Africa. And then if you want to know what the probability of the word will is, given that it's preceded by all of these words, then what you can do is you can count up how often does the sequence on day 0, the water in Cape Town will, how often does that sequence occur out of all the sequences that we have that has on day 0, the water in Cape Town. Okay, so if we count up out of all the sequences starting with this, how many of them end with the word will, then we can estimate the probability of the word will given that we have these preceding words. Okay, and I use this notation C here to indicate the count of words. Okay, now this actually turns out to be the maximum likelihood estimate for these conditional probabilities. Okay, so that's really nice. All we need to do is we need to collect a large amount of data, and we need to just basically count up all these sequences and keep track of all of these different counts. The problem is, of course, that if we actually do this in the real world, then most very long sequences will never occur. Okay? And the question is, should we just then say, okay, well, this has never occurred before in my little training data set of, well, even my big training data set of text, this sequence has never occurred before, so I'm just assigning it a 0 probability. That's probably not a good idea. So this corresponds to this problem of sparsity, where in real language, we are often just dealing with things that we've never seen before, or maybe we've seen it once, or if we're lucky, twice. But in most cases, most events will actually be quite rare. And we don't necessarily want to assign a 0 probability to sequences like this. And that's a long-winded way of saying we need some assumptions that we need to build in. Just doing this naive maximum likelihood approach won't cut it. We probably need to simplify things a little bit so that we don't have to keep track of these enormously long sentences, which are unlikely to occur anyway. N-gram language models are one way to make an assumption. Let's simplify this a little bit. I'm going to use the running example from the WhatsApp screenshot that you saw a few slides ago. And there the question was, what is the probability of the word maybe, given that it's preceded by are you keen to? Okay, we want to know that probability. And what I've said before was the naive approach would be to count up how often does are you keen to maybe occur out of all the occurrences of are you keen to, and that would give us the maximum likelihood for this probability. But we've seen that could be problematic because maybe in all of my WhatsApp messages that came before it, maybe we've just never seen this specific sequence. So one approach is called a Bigram model. And in this approach, we assume that the probability of a given word depends only on the single word that preceded it. In this case, the Bigram assumption is basically going to say, well, maybe only depends on the single word that preceded it, which is the word to. And given that I know the single preceding word, it's conditionally independent of the stuff that came before it. Okay, so in that case, we would have like the probability of the word maybe, given that you have the preceding words are you keen to. The Bigram assumption says that this is approximately equal to P of maybe, given that we only look at the single preceding word, which is to, and this is the Bigram assumption. Okay, so the Bigram assumption says, given the preceding word, this current word is conditionally independent of everything else that came before it. So we don't have to look at these words in order to calculate this specific probability. Mathematically, that means that the probability of the current word given everything else that came before in the sentence, that is approximately equal to the current word given only the word that came before it. And that's the Bigram assumption. We still have to decide how we're actually going to calculate this. And there's a number of ways in which to do this. And we'll look at smoothing techniques and more complicated approaches in the following video. But one option is to just use the maximum likelihood estimate for bigrams, which in this case would correspond to counting up, in our little example that we're looking at, the bigram maximum likelihood estimate of the word maybe preceded by 2, that is equal to the count of how often 2 maybe occurs out of the counts of the word 2. Okay, so this is the maximum likelihood estimate for this particular bigram, where we have the preceding word 2 and the next word maybe. This actually starts to address the sparsity problem, because the words 2 maybe and the word 2 is much more likely to actually occur in our little training set maybe of my previous WhatsApp messages. And we don't have to keep track of these extremely long sentences that are actually unlikely to occur. We could have actually gone even simpler. So we could actually make the assumption that every word just occurs independently of whatever came before it. Okay, so we could make the assumption that the probability of maybe, given that we have the preceding words, are you keen to, that this only depends on the word maybe, and that it's actually independent of what came before it. And in this case, that would mean that you're just calculating what we call the Unigram probability of the word maybe. Again, we need to decide how we're actually going to calculate this. And in this case, the maximum likelihood estimate is just the count of the word, in this case maybe, out of the total count of words in my data set. Okay, so we end up with a little equation like this. Out of the total count of word tokens in my data set, how many of those tokens correspond to the word maybe? And that gives us the Unigram probability. Now, this is actually quite a crude or a dumb model, because if you shuffle the data, so you take all the sentences in your data set and you just shuffle them randomly, like swapping out the word order, messing up the word order, then you would actually still end up with exactly the same estimates. So this is sometimes called a bag of words model, because you can take all the words in your training data and shuffle them and calculate the probabilities, and you still end up with the same estimates for the different words. Now, despite being somewhat crude, for many applications it actually turns out that the bag of word assumption, or the Unigram assumption, is perfectly fine and you can use it. So we've gone a little bit more simpler than a bigram approach. We could also go slightly more complicated. So in a trigram model, instead of saying, like in a bigram we only look at the preceding word, in a unigram, we only look at the current word. In a trigram model, we basically say, well, maybe we can estimate this probability by looking 2 words into the history. So the current word might depend on not just this preceding word, but also the word that came before it. So maybe we have the probability of the word maybe, given that the 2 preceding words we're keen to. Okay, but given that we've got the 2 preceding words, we don't have to look further back into the history. And in this case, the maximum likelihood estimate would be the count of keen to maybe out of keen to. Okay, and that would be the maximum likelihood estimate for a trigram model. Okay, so what I've summarized were bigrams, unigrams, and trigrams, and all 3 of these are actually special cases of the general approach, which is N-gram language modeling. And in the general case, what N-gram language modeling says is, when I'm looking at the current word, I just have to look back to the N-1 previous words. Okay, so for a trigram, N is equal to 3. And what's happening is, when we have a N-gram model, the trigram model, when N is equal to 3, then we just have to look back at the two preceding words. Okay, and we would write it out like that. But for the general N-gram case, where maybe N is 5, so we have a 5 gram or a 4 gram, we look back at the N-1 previous words. And again, even if we make this assumption, we still need to decide how we're going to estimate these specific probabilities. And one way to do that is to use the maximum likelihood estimate, where you count up basically out of the N-1 preceding stuff, how often did the sequence of N words occur in my training data. Now, all N-gram language models are Markov models. What does that mean? A Markov model, or the Markov assumption, that basically says that when I'm trying to predict something, I only have to look back a finite number of steps into the history. I don't have to look back all the way right to the start. We can predict the probability of some observation by only looking back a finite number of steps. We've looked at unigrams, and in unigrams, N is equal to 1. Okay, this is equal to 1. In bigrams, N is equal to 2. And in trigrams, which is actually written down here, N is equal to 3. Okay, we can also try N is equal to 4, 5, 6, and so on. The question, of course, is what is the value of N that I should choose? If you have a higher N, you get the advantage that you're actually taking into account a longer context. You're looking back, further back, and that might give you a more accurate prediction for the word that you're looking at the current position. But the problem is that you run into sparsity issues. If you're trying to keep track of very, very long sequences, they are actually unlikely to occur in your training data. If you have tons and tons of training data, maybe that's okay. But at some point, you're going to run into sparsity issues. A smaller N has the advantage that you struggle less with sparsity because you are just having to count up things that are shorter in length, so they're likely to occur in your training data. But now the problem is that you're actually taking less context into account in your language model. So there's this trade-off, and ultimately you're going to have to make a decision in some way, and that might depend on the amount of training data that you have, but also the downstream application that you're looking at. Later on, I will also explain how you evaluate language models, and often a good approach is to use some validation data, as we normally do in machine learning, and you get these counts from some training data, and then you evaluate your N-gram language model on the validation data. And then you can try maybe a bigram or a trigram or a 4-gram or a 5-gram and so on, and you pick the one that has the best performance on this held out data set, which you didn't use for getting your counts.